Okay, so let me start. So in the last session, we left the place where we tried to find out what was the SALC, right? So very quickly, if we go across, then so this was the reducible representation for the SALC. What we took the basis was one is A and one is B, and this like you can based on these bases, we can generate the reducible representation. Now, last class we did with matrix representation. Now here also you can apply the unshifted rule, right? So it's like if this orbital changes the location, then it is 0, otherwise it is 1, right? So if we can do that in that way also. So for identity, so both of them are going to be remaining unchanged. So this is going to be 2. Then if I do C2 along Z, then it is going to be both of them are going to change their location. So this is going to be 0. Again, sigma b xz plane, that is the xz plane. So we can get it to 0 because both of them are changing. Now, if we go for sigma b yz, then both of them they remain on the same plane. So therefore, this is going to be 2, right? So now, if you reduce this, of course, last class what we did, so that is going to be A1 plus B2, right? B2 is going to be the one which is having 1 minus 1 minus 1 1, right? So so that means it indicates that if we take the basis, then basis one is A, one is B, then we will be getting 2 of the SALC. One of them is going to be A1 type, another is going to be B2 type, right? So what is going to be their representation and or how they are going to look like? Let's do it, right? So we already did it in the last class. So I'm just going to go quickly. So this was like if we do all the operation on the one is A, then we are going to get something like this. This remains so one is A, right? So again, if I do C2, then this is going to be one is B, right? This is going to be one is B because it's going to change, and this is going to be one is A, right? And then character for A1 is going to be 1 all of them. So that means it's going to come up here itself, and then if we sum them up, then what we get is basically SALC of A1 type. And I'm not repeating this. After normalization, what we get, this is going to be 1 by square root of 2. 1 is A plus 1 is B, right? Now, this, of course, you can understand is going to be a kind of dumbbell shape because one is A and one is B. When you take the overlap, positive overlap, so that is going to be something like dumbbell shape. It's going to be like that, right? So that is plus combination. Now, if we go for the of course, last class somebody asked that if, why should not we use the another basis. So its answer is basically whichever basis you take, answer is going to be same, right? Now, of course, you can ask another question like, why do we take only one is A? Because this is one dimensional, right? A1. So one basis is going to be sufficient to generate. So we don't need to really go for the other basis. But we'll see if we have a higher dimension, then maybe we need to go for other basis also, right? So that is the idea. Right, now if we go for B2, that is just change a little bit. So B2, this row remains same. It's no change, except that this one is going to be minus and this one is going to be minus, right? So I'm removing this also because I need, sorry. So this is going to be minus 1, that is the character for B2, right? Now, if we do this, then this is going to be 1 is A. This is going to be minus 1 is B. And this is going to be minus 1 is B. And this is 1 is A. Right. So then if we take the sum, then what is going to be? It is 2 into 1 is A minus 1 is B. And after linear combination, then this is going to be a minus combination. Of course, this symbol is going to change. So therefore, this is going to be B2. Right. So that is the SALC what we get. Right. So we get two SALC. One is A1 type, another is B2 type. Now, the AMO, the SALC using this negative combination, what we are going to see is going to be like this is plus. If we take, then this is going to be minus combination. So we are going to get a node along this, right? So that tells you that this is going to be negative combination. It's like a kind of also kind of dumbbell shape, but it is like there is a node along this. There is no electron density in between, right? So that's what all of you know, all these things. So these are the two SALC what we get from the projection operator, right? So now the idea is that these two SALCs are going to be combined with the atomic orbitals of the central atom. So that is oxygen, right? So therefore, we need to find out also the symmetry of the oxygen atom. So to do that, we have to take individually the atomic orbitals, right? And then find out what is going to be their symmetry, and according to their symmetry, we are going to combine. Now, Sushrut asked last day why we did not go for this first and then SLC followed by SLC, but that is not a matter. It's like your choice which one you want to go for, but ultimately we have to combine them. So now we have valence orbitals for the oxygen only, because core orbital we assume that they are not going to take part in the bonding. Now here is the if we take this is 2s and these are the hydrogen, right? Now the good part of this is that oxygen, the central atom, is sitting on the principal axis, which is Z axis. So that makes our life simple. So what is going to be the representation for 2s, right? Now, as it is spherical, say 2s, and sitting on the principal axis, so you can imagine that this is not going to change under all the symmetry operations of the C2B point group, right? So like if you go for identity, this remains unchanged. If you go for C2 along Z, so it's just a rotation, but it's not 2s orbital is not going to change. Now if you go for sigma V, that is XZ, again there is the XZ plane is like that, so that is not going to change, and YZ of course like plane of this screen, so that is also not going to change. So therefore this 2s orbital is going to be of A1 type, right? So that is pretty obvious, you can do it. Now what about this 2pz, 2px and 2py, right? So let's do it, and you can figure it out. Now, of course, like you can do it using the character table. If you look at the character table, and you can easily say what are going to be their representation, right? So instead of doing this, let me do it first using the change, how they are going to change. So like if we go for PZ, now PZ, if we perform identity, it remains unchanged, right? So phi z is going to remains unchanged under identity. So therefore, character is going to be 1. If I perform C2 along Z axis, right? That's also same. So that is going to be 1. If we take XZ plane, so X is perpendicular to the computer screen, right? So therefore, it is going to remain unchanged, right? So that is 1. And YZ, of course, like on the plane of the molecule, so that is going to be 1, right? So the irreducible representation is going to be A1. Now PX, if you take, so the identity is always 1, no problem. Now if you go for C2, if we do along Z axis, right? So that is going to be Px is going to go to minus Px, right? So therefore, this is going to be minus 1. Now if I go for Xz, now is because this is X, so this will be on the XZ plane, right? So therefore, this is going to be a 1, right? Now if I go for YZ, right? So sigma B prime YZ, what happens? Now this is going to change to minus X, right? So therefore, this is going to be minus 1, right? So now we'll come back what is going to be the irreducible representation. So from this you can of course understand this is going to be B, of course, like one dimension, then this is going to be B, this is positive, so that is going to be B1, right? Now if I go for PY, again identity is 1, C2, Y along C2 along Z, so Y goes to minus Y, so PY going to be minus PY, so that is going to be minus 1. Now if I do sigma XZ plane, so then PY is going to be again minus PY, so that is minus 1. Now YZ plane, of course, PY will be on the plane, so that is going to be 1. So therefore, this is going to be B2. Okay. Okay. So now 2S is going to be A1. Now PZ is A1, PX, P1, and PY B2. Okay. So this we could have done using the simple character table also, but I just wanted to show you how we can do it without going to the character table also. So here also you can look at this as Z transform along A1. So PZ must be A1. Now X transformed as B1. So Px therefore should go along B1, and B2 Y transforms as B2. So therefore Py should also transform as B2. Right. So that's what we get it. Right. We can.
Sir, please unmute yourself. We can't hear anything.
Are you able to hear now?
Yes, sir. Now it's clear.
Okay. So yeah, so that is Pz. If you look at the character table, it goes along A1, right? So that is A1. Then Px is going to be B1, and Py is going to be B2, right? So that's what we did a couple of seconds back, right? So now that we have SALC of different types and the central atoms also, this was 2s, so that was also my A1, right? So we need to take their symmetric consideration and combine them, right? So if we look at it now, so that's what I have placed them. So the symmetry species for C2b, that is A1, B1 and B2. Now then SALC, if we are considering SALC of A1 type, is going to be this. Then A1 atomic orbitals of oxygen are going to be 2s, 2pz, right? Now B1, I don't have any SALC, but I have atomic orbitals of oxygen, that is 2px. Now B2, I am having this SALC negative combination, and I am having Py. So if we now need to form the MOs of A1 type, so I need to combine these three orbitals, one SALC plus 2s and 2pz, right? So that means I'm going to get MOs of A1 type. So I'm writing in small a1, which is going to be basically the linear combination of, let's say, C1. Then I am having to have psi A1 plus C2 2s. So when I'm writing 2s, means it's basically the functional form. It is a function. You have to remember that. Then I am going to have C3 and then 2pz. Right. So this is going to be a MO of A1 type. Now you look at here, I'm having three coefficients, right? So the beauty of the linear combination is that now it does not depend on the basis. Now it changes in the form of the coefficient. So if we apply the energy minimization, what we get a secular determinant which is 3 by 3 secular determinants, and if we solve that, we get non-trivial solutions for C1, C2, and C3, and then we combine accordingly, and we are going to get 3 MOs. Right now, B1 I don't have SALC, so B1 for oxygen atom is going to be non-bonding, so that is 2px. Now B2, again I'm going to combine this, so that is going to be B2 type. If I combine, so that is going to be, let's say C4. These are arbitrarily I just chosen. There's nothing like there is no rule. That is a combination of B2 psi B2, that is SLC, plus C5 of 2py function of oxygen atom. Right. Now here again, if we again follow the energy minimization, we'll get 2 by 2 secular determinant, and if we solve it, we get 2 coefficients like C4 and C5, and then depending on the coefficient, we get 2 MOs. Right. So overall, we get 3 MO for A1 type, 2 MOs for B2 type, and 1 is going to be non-bonding, which is this for the oxygen. Right. So let's see how we can combine this and find out what is going to be the MO. Right. So here we go at oxygen atomic orbitals 2s. We just arrange them according to energy. That is A1 type, now 2pz A1, py B2, and px B1. Right. Now here is the atomic orbitals of hydrogen. So this is 1s, 1s. So when we form the SALC using the symmetry adapted linear combination, we get this is plus combination and this is minus combination. So these are 2 SALC. Right. Now when we combine, we have to remember the 2 things. Similar orbitals are going to combine, so that means they should have the same symmetry first. That means I am going to look for A1, whatever is there. This is A1 and this is A1. I'll combine them. And second thing is that their energy has to be comparable. That means this, if this SALC would have been somewhere here, like this place, then we really may not have option to combine all 3 of them. Right. So 2 things, symmetry and also the energy you have to consider. So if we do that, so for this 3 combinations, so I'm going to get 1 orbital, let's say here. So that is first one. Then 3 orbitals are going to give 3 MOs. Second one is going to be somewhere here, and third one is going to be let's say it's going to be there. Right. So this is A1. Right. So this is also A1, and this is also A1. Right. Now, how they combine? Now this and this PZ, they combine. So if you just connect like this one and this one. So a more contribution will be from this, and PZ will be very less contribution. So the coefficient will be less. So this is going to be something like a combination of 2s of oxygen and this SALC, right? So shape is going to be something like this plus this. So that means at oxygen, this is 2s, and then you have SALC plus combination, right? So that is going to be something like this. So this is my drawing is not good, but you can think about this. All are positive, so it looks like this. Right. Now this is again is going to be combination of mainly this and this period. This contribution is going to be less, and of course this is going to be more with this, this and p set, this will not be there that much contribution, right? So that is the way we're going to combine, right? So the structure for the timing I'm not drawing. We can draw it like, okay, let's say do it for this one. So if we take this and this pz, so then I'm going to be having something like this, two of them. Then I'm having pz is going to be this and this. So now you can think about, this is going to be, of course, negative combination, right? So that means this is, if you are taking, this is plus. Plus means, because if you look at here, this is plus and this is minus. So now I'm taking negative combination. So this is going to be plus. So this is plus and this is plus. This is plus, but this is going to be minus. So that is kind of shape we are going to look at, right? So that we can work it out if we get time. It should have could have done this, but this is the strategy how we do this, right? Now px, we don't have b1 here, so this is going to be kind of non-bonding px. So that is b1, right? Now I have this b2 and this b2. So if we combine them, so we should get two of them, right? So if we combine them, so one will be here somewhere, right? Let's say, and another is going to be somewhere, right? So that is b2 and this is also b2. Okay, so this b2 is coming from here, it's connected to this, and I'm going to go like that. Okay, now so these are again this is a1, so this is connected with this and something like this. This a1 is also like that, and this one, if you wish you have small contribution, I should connect this also, right? So that is kind of this. Now you fill up the electrons, then you're going to get the idea, right? So you have 2 electrons here, then you have 2 electrons here. How many electrons you are going to get? Total 4.